So now let's talk about the last modification. Okay, this is what we call as the regenerative vapor power cycle. Now, let's look at this TS diagram here. Okay, and consider the superheat cycle, right? So talking about one dash, sorry, let me just draw it neatly. Talking about the cycle from 1 dash, 2 dash, 3, 4, and 1 dash. Okay, the one that I've drawn on the on your screen. Now, when you look at the cycle, uh, we see that the heat addition is happening between the the states 4 and 1 dash, right? Heat addition happens from 4 to 1 dash. Okay, and the thermal efficiency formula is 1 minus Tc by Th. Now we have looked at several ways in which we could either reduce Tc or increase Th and thereby increase the efficiency. So now again we're going to look at one last way of increasing Th, but this is a very interesting way of increasing Th, and we'll see how and why is it different. So here, when you look at this process 4 to 1 dash, we can see that this part here, right, the one from 4 to A, this is actually a low temperature part, or this is the part where the heat addition is happening at a low temperature as compared to the rest of it. So since this is a relatively low temperature part, it brings down the average temperature of heat addition. Now, to give you some numbers and to give you an idea about why do I call it low temperature heat addition. Now, the temperatures that for the pressures that we looked at in the previous example, let's say 80 bar. For 80 bar condenser pressure, at state A, the temperature is already about 300 degrees Celsius. Okay, state 1 dash, let's say it's 400 something, 480, 440, whatever you wish. But at state 4, right, the temperature is about 40 degrees Celsius, or at max 50. So you can see that from state A to state 1 dash, the average temperature is pretty high, it's 300 plus. But from 4 to A, the average temperature is pretty low. I mean, if you're looking at, let's say 40 and 300, we're talking about an average temperature of, let's say, about 160, 170, right? So it's pretty low as compared to the rest of it. So what we want to do is we want to find a way in which we can increase the average temperature at which heat is being added, or in very simple terms, instead of sending the water to the boiler at state 4, which is at a low temperature, I want to somehow be able to heat it up and send it at a slightly higher temperature. Okay, I want to increase the average temperature at which heat is being added. All right, and why do I want to do that? Well, because from efficiency formula, I know that if I increase TH somehow, I will be able to increase the efficiency. So we already looked at different ways of increasing TH. This is one last way of increasing TH. Okay, and the way we do that is we said we want to increase the temperature at which the water is entering the boiler. Let me call this 4 dash. Okay, the point that I've drawn here. Now, if I want to increase the temperature of the water entering the boiler, I need to somehow heat the water at state 4. And the way it is done in most power plants is that uh, you you allow some part of the steam to expand, right, within the turbine, but at some midway pressure, right, you don't allow everything to expand all the way to condenser. You expand you expand all of it to expand to a certain pressure, right, some midway pressure. Let me call this 2 double dash, and then at this point you extract some amount of steam. Okay, and we send it through heat exchanger where we use it to heat up this water coming out from the pump. Of course, the rest of the steam we allow it to expand within the turbine. It goes to the condenser and so on. So in really simple terms, we're using some really hot fluid coming from the turbine, and we are making use of it to heat up the water at the inlet, at the exit of the pump. Why do we want to do that? Because we want the inlet to the boiler to be at a higher temperature. Okay, again to increase TH and increase the efficiency. So if you look at it, what we are actually doing is we are actually by not making all the steam to expand within the turbine, we are reducing the net work output of the turbine. Okay, it's going down a bit, but when we are doing this, we also will need less heat input because the temperature of the water entering the boiler is slightly higher. Okay, whereas the exit temperature is the same. So till now, when we were looking at any modification such as superheat or reheat, superheat, reheat, or even increasing the boiler pressure, or in all such cases, we had to increase heat input to achieve higher work output. Okay, both were increasing. And of course, the amount of heat input you had to increase was slightly smaller as compared to the network output you were achieving, simply because efficiency was going up. Now we're doing the opposite. We are again increasing the efficiency, but we're doing that by reducing the network output and reducing the QN. Okay, so this is something that's happening in the opposite direction, but it's a very interesting way that we are able to increase the efficiency throughout. Okay, so of course the amount of work output that reduces is small as compared to the heat input that reduces. Okay, which is why we are having an increase in efficiency again. But just to kind of compare and contrast between this and the other systems, here the work input would reduce when you do this, right? Because you're not allowing all the steam to expand, you're taking part of it, but the heat input also reduces. So this is a very smart way, and this is a very interesting way that would not normally come to mind, right? If you want to increase the efficiency, you may just think about, more heat, more work, and that's it. But this is like doing the opposite direction, but increasing the efficiency, which is pretty important. Okay, now I said we just do this by using a heat exchanger. So the heat exchanger where the water gets heated is called it's either called a regenerator or a feed water heater, and it's simply called a feed water heater because it's heating the water that is fed to the boiler, right? So the water that at the exit of the pump is the water that goes in and goes to the boiler and so on. So the name of the water that goes in that is fed into the boiler is basically called feed water, and that's why we have the feed water heater definition here. So as I said, feed water heater is simply a heat exchanger. Okay, so you have to somehow transfer heat from steam to the feed water coming from the pump. Okay, so now you can do that in two different ways. You can either have a direct mixing of the two streams, right? Or hot and the cold stream, which is what happens in a open feed water heater, or you could transfer heat without any direct exchange, right? Which is what happens in a closed feed water heaters. Now, depending on what sort of heat or feed water heater you employ, the energy balance and the equations would be slightly different. Okay, and of course it brings with its own sets of additional complexities which may be needed, and we'll be talking about each of these in a minute. Now, it's important to know that this is essentially just a heat exchanger. Okay, so you either have a direct contact heat exchanger or an indirect contact heat exchanger. To give you a simple example, what we have in our um, what we have in our car, the radiator is an indirect contact heat exchanger. You have two streams which are not mixing, but they're exchanging heat. Okay, so let's talk about the first feed water heater, which is the open feed water heater or the direct contact feed water heater. Okay, so this is, I mean, we're calling it a heat exchanger, but it's essentially simply a mixing chamber. You have hot and cold fluid coming together, mixing and giving you a fluid at a temperature you like. I mean, you could think of this as the mixing valve in your shower, right? You adjust the hot and cold water to get the appropriate temperature. That is essentially what's happening here. Nothing more, nothing less. Okay. Now, let's look at this in more detail. We said we need to extract some part of the mass fraction from the turbine and so on. So let's look at what's happening in here. Okay, so here we said in an open feed water heater, we are sort of extracting steam from the turbine and mixing it with the feed water exiting the pump. Okay, so let's look at this. This part here is the feed water heater, okay, or the heat exchanger where we are having a mixing between the two streams. So let's start at state one. All right. So you start at state one, you do the expansion, and the expansion till state two is perfectly normal. It's like the one we always do. Now at state two, we separate the outputs, right? We send a fraction of the steam, which is still superheated, We send it towards the feed water heater. Okay, this is the part, fraction y, going to the feed water heater. The rest we continue to expand. So what is the rest? The rest is 1 minus y. We let it expand within the turbine. Okay, so it expands within the turbine and produces network output. Produces work output. And then at state 3, it goes through the condenser. So it rejects heat, becomes at state 4. And at state 4, we need to pump it up because open feed water heater is a direct contact heat exchanger or a mixing chamber. The two fluids are mixing, so they need to be exactly at the same pressure. And since we extracted the steam from the turbine, this is actually at a higher pressure. Okay, so you can see that the pressure here, pressure at 2 is higher than the pressure at, let's say, 4. So we use a pump and increase the pressure so that P5 is equal to P2. All right. So we bring it at the same pressure as the feed water heater. Now at state 5, it is cold, but at the same pressure as P2, and state 2 is the superheated steam. So um, you have compressed liquid at state 5 mixing with uh, super superheated vapor at state 2, and the mixing happens within the feed water heater. These are the two different inlets, right? They mix, and the output of the feed water heater is saturated liquid at state 6. Now it can also be it does not always have to be saturated liquid. It could be maybe, it could be maybe slightly compressed liquid or maybe a mixture, but we always try to ensure that it leaves as a saturated liquid. We don't want it to be leaving as a mixture at the end of the feed water heater, simply because it has to go to a pump. All right. So if nothing is given, you can confidently assume that at the exit of the feed water heater, we have saturated liquid. Okay. So it comes out at stage 6. Now this is much higher. It's at a much higher temperature than before, right? We have heated it up. It's much higher temperature compared to state 5. So from state 6 to 7, you again send it to a pump to bring it up to the boiler pressure, right? So this is the boiler pressure. Let's say 80 bar. Let's say the pressure of the feed water is maybe 40 bar. So you have to pump it up again. And once it's at the boiler pressure, now it enters the boiler at stage 7. Okay, so it heats up from 7 to 1. So, so this is what happens when you have a feed water heater. Now let's say you don't have the feed water heater. Let's say you just remove this. Okay, what would happen? If you have to move this, if you have to operate this cycle, we would not be able to stop at 5, but we would have to pump it a little bit higher and reach state 1. Okay, or state A, sorry. Once you reach state A, once you reach the boiler pressure, that's when we send it through the boiler and we provide the heat input to reach state 1. The cycle continues from there. So the difference is, with feed water heater, the heating process happens from 7 to 1. Without feed water heater, the heating process would need to happen from A to 1. Okay, so as you can see, T7 is much greater than temperature at state A. And by doing this, we're doing two things. First of all, we are reducing the heat input that's needed, but more importantly, we are able to increase the average temperature of heat addition, simply because T7 is greater than TA. So 7 to 1, the average is going to be higher than the average from A to 1. All right. So as we are increasing TH, the efficiency goes up. And that's all what we want to achieve from here. Any questions? You guys are pretty quiet today. Either you're understanding everything or nothing. Which one is it?
It's clear, Doctor.
All right, good. Okay, so this open feed water heater, or feed water heaters in general, bring their own complications in the sense that, the mass flow rate is not going to be same throughout all components. So that's the tricky part. Okay, so we have a certain fraction y going to the feed water heater. We have certain fraction 1 minus y expanding through the second turbine expansion stage. So you got to be careful when you calculate the thermal efficiencies, when you apply the energy balances. Okay, so we're going to look at how the energy balances will change for each of these components. Till now, the mass flow rate through all of those components was remaining same. So we just, took a difference in enthalpies and solved it. But now we cannot do that. The mass flow rates are going to change from one component to the other. Okay, so before we go ahead and talk about the mass balances and the energy balances for these, I just want to mention one other advantage of using an open feed water heater. It certainly increases the efficiency, no doubt about it, but it's also useful from the point of view of venting out dissolved gases or ejecting the dissolved gases that may be existing within the cycle. And by doing this, we are able to reduce corrosion. Now, what gases can get into the cycle and where do they get? Well, remember that condenser pressure is much smaller than atmospheric pressure, right? It's 0.08 bar or around there, right? So it's much smaller than 1 bar, which is the atmospheric pressure about. So since this pressure is so less, there is always a chance of some air leaking into it, and we want to remove all the dissolved gases. We don't want any sort of oxygen into this, or we don't want any oxygen or any other dissolved gases into the to remain within the system, right? And in open feed water allows us an opportunity to eject them from the system. How do we do that? Well, open feed water heater pressure is much higher. I mean, at the exit of the open feed water heater, we are reaching a saturated liquid state. So the liquid will be at the bottom. Everything else that remains, all the vapors, we just throw them out from the top. So that is one way of doing it. Now, let's look at the energy balance for the feed water heater. Now, it's in most questions, you're sort of asked to determine how much is Y, or you have to sort of make use of the energy balance from this feed water heater. So let's go ahead and determine, let's figure out how to determine Y. Or the fraction that goes to the feed water heater from the steam. So it's a very simple formula. I mean, you simply have to apply energy balance, right? I would recommend you to understand how this is happening rather than trying to remember the value for Y, because the value for Y depends on enthalpies, and what is one, what is two can change from one system to the next, right? By making some modifications. State one, state two would be different every time. So got to be careful about that. So let's apply energy balance to the feed water heater. Okay, feed water heater is simple heat exchanger. There's no work in, there's no heat output. I mean, there's no heat loss to the surroundings. So all that is happening is the change in the enthalpies, right? Coming in and going out. So when we consider the feed water heater, it has two inlets, okay? Two inlets and one output. The inlets are coming in with different mass flow rates. So you have inlet at state 2, okay, and inlet at state 5. Now the inlet at state 2 at enthalpy S2, it's coming with a mass flow rate of Y times m dot 1. What is m dot 1? M dot 1 is the mass flow rate at state 1, right? It's the flow rate here. So a fraction of it, Y times m dot 1, goes to the feed water heater, okay? So this is the mass flow rate, Y times m dot 1 times the enthalpy S2. The other input is the one that's coming from the pump. And what is the mass flow rate there? Well, you see the 1 minus Y fraction goes to the condenser, goes to the pump, and that's exactly what enters here. So it's 1 minus Y times m dot 1. This is the other mass flow rate, okay, other fraction of the steam. This times the enthalpy at H5. All right, so these are the two inputs. At the output, since the two streams Y and 1 minus Y are combining, we have again the mass flow rate equal to m dot 1 at the exit at state 6, right? So it's m dot 1 times H6. So this is the simple energy balance. Here we are trying to determine Y. So we can cancel out m dot 1 and keep Y on one side, and the other terms on the other. So I can send this H5 to the other side, okay? And this is how I can write it to be. Now I'm interested in getting Y, so I can write Y as H6 minus H5, which is the increase in the enthalpy of the cold fluid, right? On the cold side, you can say, divided by H2 minus H5. H2 minus H5 is the maximum difference in the enthalpy, right? It's a difference in enthalpy between the two inlets, which are the two inlets, state 2 and state 5. Okay, so this again is something that you should be able to obtain by energy balance. You may be provided Y and you may be asked to calculate the enthalpy at state 6, or the opposite may happen. So you should know how to use this. Now let's talk about the turbine, okay? The turbine stages. So now for calculating the work output of the turbine, it is convenient to sort of assume that the steam is expanding in two separate turbine stages, okay? Because the mass flow rate in each stage is different. All right. So for each stage, you can put m dot n is equal to m dot out and calculate the work output for the two turbine stages. So for the first stage, where it goes from 1 to 2, right, the mass flow rate is m dot 1. Okay, so when you write the mass flow rate per unit mass, so it's work done in turbine 1 by m dot 1 is equal to h1 minus h2. Now for the second stage, the mass flow rate is different. Okay, it is 1 minus y times m dot 1, or if you want, you could also write it as m dot 3. Okay, indicating the mass flow rate at stage 3, or the mass flow rate at the exit of the turbine. So I could write it as Wt by m dot 3 is equal to h2 minus h3, right? That's what's happening. Now, if you want to find out what the work output per unit mass and taking the taking the mass flow rate at state 1, which is the mass flow rate that enters the turbine actually, you can write it as h1 minus h2 plus 1 minus y times h2 minus h3. Okay, so h1 minus h2, because that's what's happening, all the mass flow rate goes from 1 to 2, but from 2 to 3, 1 minus y fraction of m dot 1 expands from 2 to 3. Okay, so for y equal to 0, that is no feed water heater, this value would certainly be higher, right? For any non-zero value of y, this value would be slightly lower, depending on how much y you send, how much fraction you send to the feed water heater. Okay, so this is one change. Same way, you'll have to be careful when you're doing the pumps. The first pump, the mass flow rate is 1 minus y times m dot 1. Okay, so that's what's going here through this first pump. For the second pump, well, the mass flow rate at state 6 is equal to m dot 1. So you already have the same stuff here. So it's a pretty straightforward thing. Okay, so for the second pump is h7 minus h6. All right, 7 minus 6 plus 1 minus y, which is the fraction that ends up at the condenser, which we need to pump it from h5 from 4 to 5. So 1 minus y times h5 minus h4. All right, so that's for the pump. Now for the boiler and the condenser, well, the boiler is pretty straightforward. At state 7, everything, at state 6, everything is combined. So from state 6 to 1, the mass flow rate is going to remain m dot 1, right? So h1 minus h7 is simply the heat input we are providing within the steam generator, and the heat input that's the heat output that's happening, or the heat rejected. Well, in the condenser we said, which is happening from 3 to 4, the mass flow rate is 1 minus y times m dot 1. So it's simply 1 minus y times h3 minus h4. Okay, so you got to be careful with the mass flow rates and how to take them, but it's pretty straightforward. In each component, what is entering has to leave, right? Both in terms of mass and in terms of energy. So you can make use of that and calculate this.